Okay, good. It's already recording. Good. Okay, so the last section in this chapter is on some properties of logs and solving equations involving them. All right, so here you can prove all of these using the exponent rules, right? And so in fact, they actually resemble the corresponding exponent rules. I'm not going to prove them for you. If you're interested in that, you can certainly look at one of these supplementary videos, but we have to make sure that we can use them. All right, and so there are only three rules of logs, right? First, if I take a log of a product, that's equal to the sum of the independent logs. So you can take the log of m and the log of n and add those together. Same way here, if I take the log of a quotient, that's the difference of the logs. So you take the log of the top, log of the bottom separately, and subtract them. And then finally, if I take the log of a power, you can bring the power down in front. Those are the only three log rules that we have. Now, keep in mind, a lot of people, like when they first see log rules, they start taking logs of expressions incorrectly. And so, for instance, a common error is to think of the log of a sum is a sum of the logs, right? So if you're adding two quantities inside here, the parentheses, you cannot distribute that log through. Same with the minus. You cannot do that. The only thing that you can simplify are logs of products, powers, and quotients. All right. Similarly here, notice that the input is being raised to the power, not the whole logarithm. And so here we'd have what often a typical error would be is to have the log base a of m, the whole thing being raised to the n, and sometimes people bring down the n. That's not what we're saying here. We're saying the log base a of something raised to that power, you can bring that power down in front. All right, so let me just illustrate these properties with these simple examples. Right, so here, the log base 2 of 4, right? Why is this true, right? So this would be an example of thinking of log base 32 and log base 8, that difference as log of a quotient. All right, so let's compute these. Let's verify that they're true. So log base 2 of 4 is 2. And then if I compute this on the other side, I get 2 to what power is 32? Well, it's 5. And then 2 to the third is 8. So you in fact get 2 again. All right, same way here, if I want to verify this is true, just compute the logs of each one and show you get a true statement. And then here, same way. Right, and so just as a verification, right? It's not a proof that these rules work at all. It's just a verification that in fact they're true. All right. Let's try these, right? So here, to simplify the first one, notice we have the log base 8 of both these guys and we're adding them. So think back here, which of these properties would I be applying backwards? I have a log base a of something plus a log base a of something. That simplifies to that same log, but of the product of those two inputs. And so here, I have the log base 8 of 2 times 4. That's the very first step, that product rule. But I know that 2 times 4 is 8, and now I can go further and compute this guy. Log base 8 of 8 is just 1, because I raise 8 to the first power to in fact get this 8 input. All right, how about this guy here? All right, so let's see if I can compute that. First, I know that I can bring this number out in front up as a power of the 3, right? Benjamin, hold on. Okay. All right, so I can bring up this 4 as a power of 3, right? And so if I do that, this expression is equivalent to log base 9 of 3 to the 4th. 3 to the 4th is 81. And so now log base 9 of 81 is 2, because 9 squared is equal to 81. Right, so these rules, if you can see, they actually are beneficial in the sense that if you apply them, sometimes we're able to get a nice simple answer rather than trying to compute each of these separately. Right, so that's one of the benefits of them. And then same way here, we have a difference of logs with the same base. Remember, ln is log base e. So that's going to be the log of the quotient of those inputs. Right, and if you simplify that inside, that's just 3x squared. So I have ln of 3x squared. All right. All right. All right, so you go ahead and try this your turn one. Same idea. I want you to simplify these just like we did before, but now using our properties. They do involve fractions, but that's the only extra little wrinkle. All right, so give those a go, and then we'll talk about them once you're done with that. All right, so let's look at the first one. You have a difference of logs with the same base. Difference of logs with the same base is the log of the quotient, right? So it's log of 2/49 divided by 2/7. But let's simplify that. Now, if you divide two fractions, you multiply by the reciprocal of the one after the division sign. If I do that, the inside just becomes 1/7. And now to compute log base 7 of 1/7, I'm just going to raise 7 to the -1 power. And so I get this back. For this guy, I can't use the product rule yet, because even though I'm adding, because there's a 3 out in front. So the very first thing I have to do is bring this 3 up as a power of the 2/3. So I do that. Cube 2/3, so that's 8/27. And now we have a sum of logs with the same base. I'm going to multiply those inputs together to get 8. And then we have then log base 4 of 8. All right, so to compute that, what number would you raise 4 to get 8? Well, there's not a nice integer, because if you raise 4 to the second, you get 16. That's too big. If you raise it to the fourth, you get 4 rather. So that's not big enough. But notice that if you cube it, you'd get 64, and then the square root of 64 is 8. So the 3/2 actually works out there. All right, so now let's go the other way. Suppose I have a more complicated logarithmic expression, and I want to break it down into sums or differences of simpler ones, right? Both these directions are beneficial for different reasons, all right? And so let's look at this. The very first one is a product of two things, namely 2 and x cubed, right? So I know that if I rewrite the inside as 2 times x cubed, I can apply that product rule property for logs to get log 2 plus log of x cubed. And then further, I have a log of a power here. I can bring that power down in front as a multiple, as I did here. Right, so I can rewrite this somewhat complicated expression as a sum of 2 very simple ones. Even better is this guy. This has products and quotients and powers all in the same thing, but I can undo all of that one at a time. Okay, now how do I do that? Well, the very first thing here is if I have a log of a quotient, that's the log of the top minus the log of the bottom. And then I focus on this piece. That's a log of a product of 3 things. So I can break it into a sum of 3 things, right? These product rules work no matter how many things you're multiplying. And so I'm going to break up the h, the y, and the z to the 4th, each of their logs being added up. And then finally, I'm going to do 2 things. I'm going to bring these powers down in front, because each one's a log of a power. So the 4 comes down in front and the 2 comes down in front. And this one, since I know the numerical value of it, I might as well put it in. Log base 2 of 8 is just 3, because I raised 2 to the 3rd power to get 8. All right, so notice that's a very compact, complicated looking log expression. It breaks down to a sum or difference of very simple ones, right? So we can go both directions. I could have started with this guy and asked you to rewrite it as a log of a single quantity. Then you'd undo each of those steps in the same order to get that. Right? You'll see the utility in particular in your calculus courses. Okay, so not only do those properties help us to compute log or to simplify log expressions and whatnot, but you can also use them to solve equations. All right, so let's look at this one, for example. All right, I have this equation. I want to solve this for x. Right. Well, if there was just a single log on the one side, I could undo a log using its inverse. Right. The problem is I have a sum of 2 logs on the left-hand side. And so what I first want to do is rewrite the left-hand side as a single logarithm. And I can do that because notice the bases are both the same. Remember, if there's no base and I'm using log, that means the base is 10. And so I can rewrite the left side using the product rule. as follows, okay? And then I'm going to undo this log by by applying the exponential 10 to something to both sides. And so I'm using these now as exponents. 10 to the log base 10 of that guy is just that input. 10 to the first is just 10. Right. But now, notice I have a quadratic equation. To solve that equation, be careful, I can't just set x and x plus 3 equal to 10, right? I have to make sure that 0 is on one side before I apply that factor property. And so what I'm going to have to do is multiply this out, so distribute the x through both terms, and subtract the 10 from both sides. Once you've done that, now I can factor this as x plus 5 times x minus 2. And if you set each one of those equal to 0 and solve for x, you get minus 5 and 2. All right, and so at this point, we have one extra little thing we have to be careful of. Remember, these x values have to satisfy the original equation. And the thing is, right here, we got rid of the log by taking by applying that exponential to both sides. And so what I have to do is make sure that if I plug these values back into the original, they make sense. And that's the struggle here, because if I plug in minus 5, right, in for x, I get a negative here, a log of negative 5, and a log of negative 2. Neither of those quantities is well defined, right? Remember, you cannot take the log of a negative number. And so what we say is negative 5 is an extraneous solution. It's a solution that you get along the way by undoing a log, but it doesn't satisfy the original equation. So you throw it out. You cannot include minus 5 as a solution. All right. But if you plug 2 in, you get log of 2 plus log of 5. Both of those quantities are equivalent. And if you apply that rule on the left, log of 2 plus log of 5 is log of 10, because you multiply the 2 times the 5. Log base 10 of 10 is in fact 1. And so 2 satisfies that equation. So it, in fact, is the only solution. All right, so that's the extra thing. You have to just make sure that they satisfy the original equation. All right, so go ahead and try this. All right, try this, solving this equation and see what you get. All right, so for this one, we're going to apply the exact same principle. We have a sum of 2 logs on the left equals a number on the right. And so I'm going to combine these two using the log of a product rule. All right, that's what I do in the first step here. And then I want to get rid of the log base 2. And so I'm going to apply the exponential of 2 to something to both sides. If I take 2 to the log base 2 of anything, the 2 and the log base 2 cancel, giving me just the input. And 2 squared is 4. Right? So I get this equation here. Again, that's quadratic. So simplify the 2 squared to get 4. Distribute the 2x through both terms to get that guy. Take everything to the left. And then what you get is this expression, which you can pull a 2 out. And then you can further factor that trinomial as x minus 1 times x plus 2. Right, so since that product is 0, we know that x is either 1 or negative 2. But remember, what do you have to do? You have to go back to the original to make sure that they satisfy the original equation. And the problem here is that if you plug in minus 2, you get a log of 0 and a log of a negative. Neither of those quantities is meaningful. And so you throw out minus 2. If I put 1 in, I get log of 1, or log base 2 of 1 plus log base 2 of 3, right? And then if I were to apply our property to that, you combine those into a log of a product, and that product gives you 2. 2 to what power is equal to 2? 2. All right, so you only get that one solution back. Oh, pardon me. Wait a minute here. So this equation here does not, these don't match up. So I think I solved a different equation. I'm sorry about that. So forget about this one. I was noticing it didn't make sense. If you plug the 1 back here, you get 2 and 2 there. Log base 2 of 4 is equal to 2. That's fine. Sorry about that. All right, go ahead and try this one and see what you get. Same idea. But now make sure you get the logs on both sides of the equation first. All right, so in this case, I'm going to pull the log of x plus 3 to the left to get that guy. But remember, the difference of logs of the same base is now the log of a quotient. And so I'm going to rewrite the left side as the log of x plus 2 over log of, or over x minus 3. That's equal to 2. But I want to get rid of the log, right? And there's no base, and I'm using log, so the base is 10. So I'm going to apply the 10 to exponential on both sides. That gets rid of that log, and I have 10 squared on the right. That's equal to 100. But now I want to solve that rational equation. So what I'm going to do is multiply both sides by x minus 3 to get that. And then I'm going to solve that resulting linear equation by multiplying through by the 100, getting the x's on the one side and the numbers on the other. And now ultimately, if you check out the detail, you get 302 over 99. Okay. That's a solution because if you plug it back into the original equation, all things check out. And so you get a solution back. All right, so let's go on. So those are just some typical log equations to solve. You can also use logs to solve exponential equations, right? So here you have exponentials on both sides, but they have different bases. And so what I can do, I'd like to be able to solve that for x. The thing is, you can't kill both exponentials at the same time, right? In other words, you can't just wipe them out. You'll still have something in terms of logs in the equation. And so what I'm going to do here, let's just suppose I want to get rid of just both of them, but I want to be able to estimate the solution on my calculator at the end. The only two buttons you have on your calculator that don't require extra work are the ln button and the log button, the log, which is base 10. So what I'm going to do here is I'm going to apply the ln to both sides. Okay. If I do that, remember you have that log of a power rule. If I have the log of a power, I can bring down the power in front. And so I'm pulling down the x plus 3 power in front and the 2x plus 1 power down in front of this guy. All right. So now I have a linear expression times a number, another linear expression times a number. I'm just going to distribute that number through, right? Remember, ln of 2 is a number, right? And so you could even put it in the calculator to see what the decimal approximation would be, if that makes you feel better with it. But it's a number, and so I'm just going to multiply it through on both sides of x plus 3 and multiply it through both terms of this guy as well. Now that is a linear equation, right? You have a number times x plus a number equals a number times x plus a number. So I'm going to gather the x's on the left, the other numbers on the right, right? That's what I've done here. I'm going to yank the x out like I normally would, and then I'm going to divide by that coefficient of x, right? And so this turns out to be the solution. Huh? So it looks weird, but if you were to compute, or if you were to plug that expression into your calculator and push equals, you'll get a decimal approximation for x. All right, so the log properties here enabled you to solve an equation that otherwise was unattackable with just our exponent rules. All right, I'm going to have you, I'll let you look at this. This is just a exercise that helps you to emulate the steps in the previous example. All right, so I'll try applying log base 2 up here instead of ln. The only difference is you'll be able to simplify this side a little nicer. All right, but there's a drawback as well. Namely, you won't have the numbers you have down here will involve log base 2, and there's no nice button on the calculator for log base 2, right? So there's give and take, but try that one. Try applying log base 2 and see what you get in the end. I'll leave this up here for you to compare. All right, and I've already spoken about these common fallacies, right? So you can't take the log of a sum and get the sum of logs or the product of logs and whatnot. So what your turn 5 is, and I don't actually do this for you in here, it's to actually plug numbers in to show that these are in fact false, right? So just to get you used to the idea that there are only 3 rules, it's really helpful and educative to actually go through and show these are false. All right, and that brings us to the problem set. So this problem set will take you longer only because you have to get used to the log rules, right? So they start off simple, just rewriting expressions as single logs and then expanding more complicated ones. This is just applications of the right log rule at the right time. Then you have a bunch of equations to solve. Be very, very careful with extraneous solutions, okay? And then here, same thing. This is more what you'll bump into in your other courses, right? You'll have formulas. This is for growth, like continuous or interest compounded continuously. Other sort of things arise in other sort of science and econ courses. So these are exactly the same idea. It's just now the other letters represent numbers. So treat them as such. Okay, and there are a couple other problems here. This one isn't too bad. This one just involves the power, the properties as well. All right, so give them a go. Take your time through them and see how it goes. Let me know. All right, take it easy. Bye.